Hello. In this video we're going to talk a little bit more about absolute value functions, try to understand their nature a little bit. This might be a little long, but please be patient. There's lots of good information here, I hope. What we see here is a comparison of y equals the absolute value of 2x versus 2 times the absolute value of x. The question is, of course, are they the same? Easiest way to answer this question would be to go to the Desmos and graph it up. So what I see in the graph here is I put in both functions, and what I see in red and blue turns out to be purple because these graphs are one and the same. So really, if I thought about what's going on here, it's really the absolute value of 2 is 2, so inside or outside it doesn't really matter. What appears to be happening is I'm able to separate or pull apart the absolute value of a product of two numbers into separate absolute values, and then since the absolute value of 2 is 2, I can just take it out and leave it alone. Producing the same graph, generally getting the same solutions, so these are equivalent expressions. Before you make too many assumptions, though, what if we had a situation where there was a negative coefficient inside the absolute value? I got a little ahead of myself here with the slides. First of all, the first inclination for some might be, if you can take the 2 out of the absolute value, can you take the negative 2 out of the absolute value? To examine this, we're going to go to Desmos and take a look, and if I graph negative 2 times the absolute value of x, I get all negative y values, whereas if I graph the absolute value of negative 2x, I get the same graph as I did over here. So really what's going on is, if I follow the same pattern that I did over here, I'm just taking the absolute value of negative 2 times the absolute value of x. I'm separating the two. So I'm going to take the absolute value of negative 2, and the absolute value of negative 2 is 2. So really, this graph right here is the same as 2 times the absolute value of x. So this exploration leads us to this conclusion. There's a fact, and that fact is the absolute value of two numbers multiplied together is the same as multiplying the absolute value of those numbers separately. In other words, the absolute value of a product is equal to the product of absolute values. Turns out to be a helpful tool for us when working with graphing and understanding graphs of absolute value equations. We looked at in class what happens when we have a coefficient on x and a walk at home to the left 6. And it turns out that this is not going to be a shifted absolute value function to the left 6, it's going to be shifted to the left 3. The easiest way to see that would be to factor out whatever the slope is from each term. So here I factor out a 2 from the 2x and the 6 as such. And then I apply the principle that we just explored, and I'll take the absolute value of 2 separately from the absolute value of x plus 3. In other words, I can simply factor out that coefficient. Even if the constant term, the y-intercept value, is not divisible by 2, we can still factor out the 2 simply by dividing 5 by whatever that is. So half of 5 is 2.5. I take that out, take the absolute value of the 2 and bring it out, and so this is now an easier to understand in graph function. In both cases, now we can see the slope of the rays are going to be 2 or negative 2, and the shift to the left of the absolute value is going to be left 3, not left 6. Or here in this case, shift right 2.5, not right 5. So one of the things I asked you to do is to practice by graphing these functions here. Use a similar technique. That technique would look something like this, if we can get to the right place. If we had to graph the absolute value of 1/2 x plus 3, I'm going to factor out 1/2. This is going to get a little tricky for some, but look at what happens here. I factor out the 1/2, which means I'm dividing 3 by 1/2, and I'm dividing 1/2 x by 1/2. 3 divided by 1/2 is actually 6. For those of you doubters out there, just take 1/2 and redistribute it, 1/2 x, and then 1/2 times 6, and 1/2 of 6 is 3. Now I'm going to take the 1/2 out, show it a good time, and here we can see the analysis of this particular absolute value graph is going to be shifted to the left 6, not to the left 3, but to the left 6. And the slope of each ray is not going to be 1, it's going to be 1/2, or negative 1/2, depending on which side of the absolute value we're on. So, from shifting from the origin left 6, I'm simply going to count my slope 1/2 over 2 up 1, draw the line, do the same thing in the other direction. Then I label a couple of points to show I'm legit, and also I can count over 2 up 1 over 2 up 1, and be sure that my y-intercept is going to be at 0, 3. Now I finally examine the rays that exist here, and I recognize this has a slope of 1/2 by design and a y-intercept of 3, so it represents this equation, y equals 1/2 x plus 3. The other one has the opposite slope, negative 1/2, and if I extended the line out, I would see it was at negative 3. To verify this is true, we look at the algebraic approach to absolute values, and notice that in one case I'm going to remove the absolute value, leave everything inside alone, y equals 1/2 x plus 3. And in the other case I'll remove the absolute value and take the opposite of everything inside, y equals negative 1/2 x minus 3. And here again we can see that this purple part is only for when x is bigger than the vertex, and the green part is for when x is smaller than the vertex. Just to show quickly another analysis, we're going to have a graph of an absolute value function that's shifted right 3, but this time the slope is not going to be plus or minus 1, it's going to be minus or plus 1. That is to say, because we have all positive numbers from absolute value, but then we're going to turn around and make them all negative, we're going to see the graph that's going to be negative y values. And once again, we can see the same analysis between the rays. This one has a slope of, that one went really fast, sorry. Just a quick talk through here. This has a slope of negative 1, and I extend the y-intercept to find out that it's probably going to be 3 based on the slope and the x-intercept. So this is negative x plus 3. Whereas this one has a slope of positive 1 and a y-intercept of negative 3, so that's y equals x minus 3. To verify this with our algebra, notice that in the first case, when I remove the absolute values, I distribute then the negative 1 and get negative x plus 3, confirmed by my graph. In the other case, when I remove the absolute values, I take the opposite of everything inside. So instead of positive x, it's negative x. Instead of negative 3, it's positive 3. Then I distribute the negative that was outside, producing the line y equals x plus 3. So all of this, of course, is verifiable by using technology. But I was going to say, well, here, I'll save it for the end. In this case, we're going to explore what happens when we do all three of these transformations at once. We have a slope change, we have a shift left, and a shift up. So identify each of those, and then try to imagine what it's going to look like if you take an absolute value function, shifted it left, shifted it up, and then squeezed it so that it was more steep. It would look something like this, just a quick little sketch. Remember the angry cloud. Now over here, we can start with where the vertex is now going to be located. We had to walk away from home, left 1, up 4. Then I have a slope of 2, so I count over 1, up 2, and get the y-intercept of 6, so that was a nice bonus. And then I do the same thing in the opposite direction. I go back 1, up 2. I label a couple of those points, identify the equation of the line from the slope and the y-intercept. So again, in this case, slope is 2 by design, and the y-intercept is 6. And over here, the slope is negative 2, and I extend out to find the y-intercept of 2. Verify using our algebra. We can separate 1 by taking out the absolute value, in which case we'll distribute the 2, and add the 4 to get 2x plus 6, confirmed by the graph. Here, get rid of the absolute value, get rid of negative everything inside, distribute the 2, and then add like terms, and we get negative 2x plus 2, confirmed by the graph. So this is a sort of self-checking. This is the algebraic or analytical way of looking at the two rays that make up this absolute value, and this is the transformation of graphical way. So we have a graphical, geometric, and we have analytical or algebraic. And so this is a way of checking. We don't have to necessarily put one of these points into the equation to verify that it's correct, but if you did, certainly that would go a long way to really backing up your work. So thanks for watching. Have a great day.